Hey folks, it's Mr. Byros. I'm going to do a video here for our ramp problem with friction. So we've got an object here that's sliding down the ramp. It has an acceleration of 2 meters per second squared down the ramp. The ramp has an angle of 21 degrees, and we know that the mass of our object is 4 kilograms. So we need to find the coefficient of kinetic friction, mu k, for this problem. One of the first things that I'm going to do is I'm going to actually flip my coordinate system. So if we picture taking the whole ramp and turning it clockwise, 21 degrees. So now the horizontal is the surface of the ramp as it's sliding down. And the reason that we do this helps us because now a lot of our forces and our accelerations are going to be in the x and y directions. So my acceleration of 2 meters per second squared is now an x direction acceleration because I switched my coordinate system like this. And the normal force, we know the normal force acts perpendicular to any surface, so the normal force is acting perpendicular to the ramp and it's pushing up on the block like so. So our normal force is in the y direction. Likewise, our friction, which is resisting the block sliding down the ramp, is also going to be in the x direction. So we have our acceleration of 2 meters per second squared, that's going to be in x direction, along with friction as a force, and the normal force is going to be in the y direction. Now the one thing we do have to split up is gravity. Up here on the red diagram, gravity is acting straight downwards. On the purple diagram, as we turned it, gravity is going to have both an x and a y component. And the way that looks is, from here we know that the x component of gravity is the part of gravity that's causing our object to move down the ramp. So here I'm going to put a little arrow, find some space. So Fgx is going to be the component of gravity, or the part of gravity, that is causing our block to accelerate down the ramp. Now what about Fgy? Fgy is the component of gravity that's pushing our block into the ramp. So Fgy is pushing down against the normal force, and when we draw a free body diagram, we're going to find out that those two are just balancing each other out. So now that we've kind of got our coordinate system established, and we know we're looking for a normal force upwards in the y direction, Fgy pushing down against the normal force, and in the x direction we have our acceleration of, oops, I forgot to write the number, 2 meters per second squared in the x direction. And that acceleration is the result of forces Fgx and force of friction, which is also in the x direction. Now it's worth noting this friction is kinetic. Our object is moving, so it's not static friction, it's going to be kinetic. Force of kinetic friction. And now that I've got my coordinates figured out, I'm going to go ahead and draw my free body diagram. So I said I have gravity in both the y and x directions. So here's Fgy. Pushing the object into the ramp. Here's Fgx, causing it to accelerate down the ramp. Now what I do know is if the object is accelerating down the ramp, Fgx, the part of gravity that's causing it to accelerate down the ramp, is larger than my force of friction, because it has to overcome that force and be greater than the force of friction to have the object move down the ramp. So here's force of friction, kinetic friction. And lastly, we have a normal force, Fn, pushing upwards from the ramp. Now we said Fgy and Fn need to be equal and balanced. I'll indicate that with the little tick marks on my arrows. And that needs to be balanced because our block isn't going into the ramp or getting pushed off the surface of the ramp, it's just sitting there. So gravity in the y direction here and normal force will just be balanced. So really all we have to do is consider the fact that in the x direction here, we can sum forces, and our sum of forces in the x direction is equal to Fgx. Now here I should decide what's positive and what's negative. For the purposes of this problem, I'm going to consider left to be positive. So we'll say left is positive and up is positive, just because I have this acceleration of 2 and I'd like to keep that a positive value. So FGX is a positive, and kinetic friction is acting to the right, so I'll have that as a negative. So sum of forces in the x direction is FGX, the component or the part of gravity that's pushing this down the ramp, minus the force of kinetic friction. Let's get this a little closer here. All right, so in order to do this, we need to find what FGX and force of kinetic friction are. Let's look at FGX first. So the total force of gravity, and I'm going to draw a separate diagram for gravity in green. Over here we know the total force of gravity is acting downwards. We're going to end up drawing a triangle for the x and y components so we can show the total force of gravity and its x and y components. The x component of gravity, as we have it drawn here, is acting down the ramp. So it's a component of gravity that here is acting like so. Here's FGX. That direction of that force is parallel to the slope of our ramp, or the hypotenuse of our ramp seen here. Also, part of gravity is pushing it down into the ramp. So this is what we call FGY. And it's pushing our block into the ramp, and it's being balanced by the normal force. In order to find how big these are, we can look at the comparison between FG, the total force of gravity, is in fact parallel to and in the same direction as this side of our triangle. And FGX is parallel to in the same exact direction as this long side of our triangle or our ramp. So these two angles have to be the same, which means if this is 21, this would be 69 degrees, and this must also be 69 degrees. So that means that this angle down here is our 21 degrees because FGX and FGY will always be perpendicular to each other. The x and y directions are perpendicular by nature. So this is a 90-degree angle on the corner of our triangle. So if we know this is 21 degrees, we can now write FGX in terms of the total force of gravity, which of course we know gravity is just mass times the acceleration of gravity, 9.8 meters per second squared. So over here in black, I'm going to do that, and I'm going to say that FGX is equal to, I'm going to do the sine of 21 degrees, because here's our angle of 21, FGX is opposite to that 21 degree angle, so FGX is equal to the sine of 21 degrees times our total force. Our total force is the force of gravity, mass of 4 kilograms times 9.8 meters per second squared. All right, so I'm going to do that math, get a calculator. All right, so we need to do the sine of 21 degrees. And then we'll take that and multiply it by 4 kilograms and multiply that by 9.8 meters per second squared. So 14.05 newtons is our FGX. Now, in order to find the force of friction, here, the kinetic friction, we need to know the coefficient of kinetic friction, which we do not yet know. We also need the normal force, and we can find the normal force because this normal force, Fn, is equal to the y component of gravity, which is, as we can see here, just the cosine of 21 degrees times Fg. So just like we did with FGX, we can say that FGY, which is also equal to the normal force, because the two of them are equal and opposite, they're balancing each other, is equal to the cosine of 21 degrees times 4 times 9.8, which is 39.2 newtons. So cosine 21 times 4 times 9.8. Let's see what we get from that. 21 cosine times 39.2. So we got 36.6. All right, so our FGY is equal to 36.6 newtons. All right, and that's also equal to our normal force. So we're getting really close. Now in purple, I can rewrite here, this is equal to FGX, which I know is 14.05, minus the force of kinetic friction, which is just mu k, times the normal force. And I know my normal force is equal to 36.6 newtons, the same as FGY. Now, how am I going to find mu k if I just don't know any of this other stuff? Well, I know the sum of forces in the x direction by Newton's second law must be equal to the mass of my object times its resulting acceleration in the x direction. In this new coordinate system that I have, my AX, acceleration in the x direction, is 2 meters per second squared, which was given to us. And we also know the mass is 4 kilograms. So I can take all of this here and set it equal to, do it over here, I'll set it equal to 4 kilograms times my AX, which is 2 meters per second squared. So what this allows us to do is say that the total or resultant acceleration of the object, so after we've accounted for gravity in the x direction, after we've accounted for the force of friction pushing back against it, when all's said and done, our object is accelerating at 2 meters per second squared down the ramp. Because we know that acceleration in the x direction is 2, and we know the mass, we should be able to now solve for mu k because we have everything else. We have the force of gravity in the x direction causing it to accelerate down the ramp. We know our normal force, so mu k should be fairly easy to solve for. So this is 8 newtons. So I'm going to take that 8 newtons, I'll subtract 14.05, which should get us, I'm just going to do this here, 8 minus 14.05 should give us a negative 6.05 newtons. And that's equal to negative UK times 36.6 newtons. Last step, of course, the negative signs will cancel out. We don't need to worry about those. And we just take 6.05 divided by 36.6. And that gives us 0.165. So, final answer, our mu k is equal to 0.165. So this is a pretty small coefficient of friction, coefficient of kinetic friction. So this surface doesn't have a ton of friction because it's a very shallow ramp, only 21 degrees. And so in order for gravity to accelerate this object at 2 meters per second squared, we need to have a fairly small coefficient of kinetic friction in order for it to be able to slide under a relatively small component of gravity, FGX. As we can see, the comparison between them, this is only 14.05, whereas the y component is a whopping 36.6 newtons. So if we had a steeper ramp, we could achieve this acceleration with greater friction, but as it is, with a shallow ramp like this, we're going to have a smaller coefficient of kinetic friction in order for this to be a realistic situation. So hopefully this was helpful. Again, walking you through it, we changed our coordinate system, tilted things so that our normal force and our friction were in the x and y directions, and the only thing we had to split into components was gravity. Then we proceeded to do that on a free body diagram, and then use Newton's second law to come up with an equation that helped us find the coefficient of kinetic friction by solving for things like FGX, FGY, the normal force, and using what we knew about the acceleration of the object in the x direction and its mass. So Newton's second law, free body diagrams, and reorienting our coordinate system, along with splitting gravity into its components, helped us find the coefficient of kinetic friction for this object and the ramp. All right, that's it. Thanks, everybody.